This segment introduces lists, which are collections of elements or values. We write the list of elements of type T by putting T in square brackets. On the left hand side you can see here I've defined a type of bills, which is a list of shop items. You can imagine a supermarket bill looks like a list of items you bought in a shop. The type of string is just a list of characters. That's how strings are represented in Haskell. And you can imagine we could also represent a type of vectors by a list of integers. I've listed some examples on the right hand side. At the top we've got the list of 7 integers, 1, 2, 3, 1, minus 2, 2, 1, in that order. That's a list of integers. The second example is the empty list, which is an empty list of integers. The third example, you can have a list with just one element. That's not the same as the element itself, which is a Boolean. This is a list of Booleans, which happens to have one element. And again, you can have an empty list of Booleans. We can build lists of functions. So the list fib, fib, that has the same element repeated, function from integers to integers, that's a list just like any other. And also we can build lists of lists. So the final example there has 3 elements. The first is the list 1, 2, the second is the empty list, and the third is the list 2, 1, 3. So that's a 3-element list, each of whose members is itself a list of integers. Now, just to reiterate, if we look at this example of the list 1, 2, 3, 1, minus 2, 2, 1, it has 7 items, some of it which occur more than once. So the number of times that an element occurs is significant, and the order in which the elements occur is significant. The first element of that list is 1, as is the last. The next to last element is 2. The value before that is minus 2. You could have those same elements in a different order. That would be a different list. So the list, the order of the list matters, the number of times each element occurs matters. So lists are not sets, nor are they bags in mathematical technology. So lists are ordered collections of values. It's important that we establish how lists are covered in this course. There are a number of different approaches people take in covering lists, and I want to take one which perhaps has not been taken so often before. Haskell has a really rich set of functions to build and split and filter and transform and do all sorts of things with lists. Also, in particular, it has list comprehensions, which we'll talk about in the next section. Now, we're able to define all these things for ourselves using recursion over lists. And one approach, which many people adopt, is to start with recursion right from the start and define everything recursively. I'm going to take a different approach, and I'm going to first of all cover lists as the API, the application programming interface, and look at the functions that are provided that we can use to build and construct and transform lists, and encourage you to use and reuse those rather than doing everything from scratch. I'd like to encourage you to reuse and write more readable code because it uses functions that are from this familiar interface. Now, one of the reasons this interface is so rich is because it contains polymorphic higher order functions. Polymorphic in other terminology is generic. So it allows us to write functions which operate over different types, or in this case, lists of different types with the same code. So they're very powerful in that they can be used over not just one type, but a whole range of types. And also they can be parameterized by functions themselves so that they can have different behavior. For example, applying a function to every member of a list to transform it in a particular way. So those are very powerful functions. We will learn about those functions before we talk about how to define them from scratch, which we will do in due course using recursion. But the approach I'm taking here is see what the functions are that we can use and reuse before we start defining everything from scratch. Now, one particular thing I want to do before we move on is just show you some very compact notation for writing down ranges of numbers. So if we want to write the numbers from 1 up to 10, we can just write 1 dot dot 10 and we get the numbers from 1 to 10. If we write 10 up to 1, we get nothing, we get the empty list. If we write 1 up to 1, we get 1. If we put in an increment, so if we say we want 1, then 3, all the way up to 10, we get the odd numbers up to 9, because 10 isn't an odd number. And we can write the up to without a limit. We can say the numbers from 1 up to forever, or 1, 3, all the odd numbers going on forever. And if you write those expressions in GHCI, it will continue to evaluate. So you need to know that if you hit Control C, that's hold down Control and hit C, that will interrupt evaluation, because otherwise GHCI will just continue to give you the list of all the positive integers or all the odd numbers. So we can write ranges of numbers that way. This isn't crucial, but I just wanted to include this information. It's really helpful to be able to do this. And in fact, it's not confined to numbers. We can do it for other types as well. We can go from false up to true. We get false and true. We can go from true up to false. Well, there's nothing there because true is bigger than false. We can go from true to true. We just get the list with just one element, namely true. We can give the list of characters from little a up to little z, and that gives us the list ABCD up to Z, because remember, strings are just lists of characters. And we can do that with an increment. And we can do this to any type that is enumerated. And we'll see some other examples of that, I think, later in the course. But I just wanted to show you these notations. But what I want to do next is talk about list comprehensions, which are a really powerful mechanism for generating and defining lists.